All right, the time is now 4:10, and I'd like to welcome our next speaker, Ryan McBee from the Southwest Research Institute. He'll be giving us a talk on deployment of machine learning algorithms on resource-constrained space flight hardware. Ryan.
Thank you very much. Go to the next slide. So a bit of an overview of what our research was about and kind of the motivation behind it. So the main goal of the research we undertook was to better understand how to deploy different machine learning algorithms on space-rated hardware. And some of the benefits, if you're not familiar with putting machine learning on the edge on whatever is in space, is faster response times to the data you're intaking to when you process it, less data transfer since you don't have to process the data on Earth, and greater security because you're not having to send the data back and forth. So it's a higher security in that standpoint. And in general, you can look at getting machine learning to go into space as two different areas to go at it. You can try and make the hardware more powerful, which is a viable option. But if you want to try and get the machine learning into space at the moment, you have to take the second approach, which is make the machine learning algorithms that you have more efficient. Next slide, please. So for our research, we wanted to kind of explore a broad area and see how different types of processors responded to different types of optimizations with machine learning towards them. So we targeted 3 different platforms and one example of a terrestrial-based platform. And we focused on a RAD 5545, which is a high-end processor that we wanted to target. We targeted a Leon 3 core, which is a low-end, more microcontroller processor. And the final platform we ended up targeting that is space-rated hardware is a Microsemi RT Polarfire, which represents our indicative FPGA. We also tested the NVIDIA TX1, which is a GPU that is roughly comparable, that is rated for Earth, but has not been shown to be usable in space. Next slide, please. So the first step in deploying machine learning in space and making it more efficient is starting with an efficient base machine learning algorithm. And luckily, there has been a lot of research in the past few years on how to make machine learning more efficient to run on smartphones, which have an embedded processor in them. And of those different machine learning algorithms, the one that was most prominent and most appealing to us was the MobileNet V2 network. And that's the image that you see below. And this network is, comparatively to the others, is simple yet effective. And it has an ability for us to kind of tune the various different layers to change the size and lessen or increase the computation based on the need that we need, which is very useful for the optimization steps that we are going to do later. Next slide, please. So as our data set that our machine learning model is trying to learn, we have 2 different data sets we focused on, both of them more satellite-based challenges. So the one on the left, the crater rim detection, is a data set of labeled crater rims that's maintained by Southwest Research Institute. And we wanted to see if we could train an algorithm to, taking in a grayscale image of the moon, could we actually detect where the rims of the crater were? And so this is an example of a single image input with a single detection output, which comparatively in the machine learning world is a relatively simple problem. And this is in comparison to what we have on the right, which is an Earth imaging satellite from an open source data set we were able to find online. That was a hyperspectral set of images. So I think roughly 7 hyperspectral images, and it had a variety of different outputs. And so you'll notice the different colors from yellow to red to green. And those represent everything from roads to buildings to vegetation. And so with more input images and more output images, this was a much harder problem and required us to use a heavier, bigger network for this. And so those 2 types of problems were compared in our research when trying to figure out how to deploy machine learning algorithms. Next slide, please. So the basic schema for optimizing this network is a pretty tried and true, but pretty useful one. where it was an iterative design of first, we would train the machine learning algorithm with the default size that was proposed for these networks and see what kind of accuracy we were able to get from them. And if the accuracy was acceptable, we would then deploy it on the actual target platform. And deploying it on the target platform is a key aspect that I would stress from this research, because a lot of research papers designing efficient machine learning algorithms and evaluating them did more of a theoretical evaluation of their effectiveness, where they would measure the total number of mathematical operations, whether that be multiplications, additions, or whatnot. And a lot of the research towards embedded implementations were referencing that you really need to be testing this on the actual platform, since every computer architecture is different and they're all going to vary differently. So that is one key aspect I wanted to stress. Once we've deployed it on the platform, we profiled the execution time. So that we, for most of our different platforms, we did it on the per layer basis. So machine learning algorithms have multiple different layers of incremental analysis that happen. And so we were able to get the performance of each different layer. We would then analyze the results at the end. And then based on those results, we would then figure out which sections seems like they could benefit the most from being shrunk without decreasing the accuracy substantially. And then we repeat this process repeatedly for each targeted hardware platform. Next slide, please. So the first platform we ended up testing was the RAD 5545, which utilized the TFLite open source software. And TFLite stands for TensorFlow Lite, which is an open source machine learning implementation supported by Google. And the main reason we wanted to lean towards using open source tools as much as we could is the ease of use, because there's a large community base and someone's already done a lot of the work for us. So that really reduced a lot of the engineering workload. But secondly, there's constant improvements being made by a large community. And so with machine learning moving as fast as it is, this is super beneficial. And in general, TFLite also supports a lot of the various optimizations and quantization of mathematics that make embedded machine learning possible. And to get the TFLite to actually work on the RAD 5545, which is a PowerPC big endian hardware, we had to actually reorder some of the memory internally from the original source code to make it work. Next slide, please. So one of the benefits of using an open source software is we had full access to the underlying C++ code that they were using. And after examining some of the different layers that were in there, we noticed that there were a lot of very optimized different sub-functions for ARM and x86 processors, which are very common. But the code defaulted to slower yet still correct generic code for the other platforms, which in our case, we wanted to run as fast as possible. So what we did on our team is we analyzed the most common cases that our neural network went through and found the layers that made the biggest difference. And we ended up trying to make specific implementations for the heaviest layers. And based on all that, we were able to make code changes that did not involve any custom assembly code, but simply just code reordering, code removal that wasn't needed for that specific implementation. And then once fed into the compiler with the specific reductions and implementations, we were actually able to see substantial speedups, which I'll show those metrics at the end, all comparatively. Next slide, please. So after kind of going through this whole iterative design, after getting the source code optimization, reducing the model, some of the general observations from trying to optimize for the PowerPC was one of the most basic optimizations for embedded platforms is to turn the 32-bit floating point to 8-bit integer math. And in most cases, that should be faster, but from the PowerPC, this actually ended up being slower. And to kind of explain why that was the case, for starters, there was a generic support for the PowerPC. So in ARM and x86, they have custom assembly code that takes advantage of SIMD instructions on those platforms. But the PowerPC does not have any of those, and it just used default implementation. So that made it slower as well. The 8-bit math actually adds some additional operations on top of the floating point to make it resemble the floating point more. And so that adds more computation time as well. And the PowerPC also supported single cycle multiply and accumulate, which helped make the floating point faster, kind of bridging that gap. So overall, the 8-bit implementation was slower, which was a bit surprising. The next observation was about half of the computation for our network took place in the very first and the very last layer. And as for some reference, this network has roughly 22 layers in it. And so the first and the last layer to take most of the time really speaks to how important these layers are. And so trying to optimize these layers, there needs to be a little bit of finesse, because while they are the most amount of time, they are also the most sensitive. So changing them can have the greatest impact on accuracy. And the final note about TensorFlow Lite is that it was relatively easy to use. Downloading it and even making the modifications were pretty straightforward for the PowerPC. And so it really did save a significant amount of engineering time using the open source TensorFlow Lite. Next slide, please. So the next platform we ended up investigating was the Polarfire FPGA by Microsemi, which utilized the Vectorblox SDK, which is also supported by Microsemi. And so the Vectorblox SDK is actually a software tool package for synthesizing machine learning implementation and also converting your models to work on the system for currently the Polarfire by Microsemi. And this actually, we were able to get it in beta release in July of 2020, and they have since made new releases. And so it's a fast and ever-changing tool that is, in our case, super useful. And at the time, we ended up testing it on the 1000 size, but they have smaller and larger sizes, just for some comparison's sake. Next slide, please. So because we didn't have access to the underlying code of this SDK, we weren't able to make the same modifications to the source code like we did TFLite. But some of the observations that we're able to make from the FPGA and modifying and tweaking the model is the FPGA, hands down, was the fastest platform that we were able to test. And this makes a lot of sense, since we can make the custom hardware and the custom logic to actually accelerate these very specific machine learning implementations. The implementation of the Vectorblox SDK that we had was missing a few of the more odd operators that we had to work around, but was definitely still capable of testing. But a lot of it, the Vectorblox software is still in development. So I imagine a lot of those operators will be supported in the near future. And in general, like TensorFlow Lite, this was a very easy software tool to use. And it definitely helped, even for someone who doesn't have a lot of FPGA experience like myself. I'm more of a machine learning guy. This tool was relatively easy to use with their system. Next slide, please. And the final platform we ended up testing was a Leon 3 core with TFLite Micro. So the specific core we ended up using was the GR712RC, which we have used at Southwest Research Institute multiple times, including the image on the right for our Cygnus constellation. And we wanted to use this choose this core because we wanted to show the implementation on a much more constrained CPU comparatively to the RAD 5545, which is much more powerful. And because we're already selling and using this processor, so give it a little bit more heritage within our company as well. And to get the machine learning system to actually work on it, we ended up using the subsystem of TFLite called TFLite Micro, which uses static memory allocation and other various tools to get the regular C++ code that runs on an operating system to run in a more embedded environment. And for our evaluation overall, we ended up using the TSIM3 simulator for testing all of this. And the TSIM3 simulator gave us a wonderful insight into the L1 cache utilization, the cache hits, cache misses, and other various inputs that we could then measure the performance and help us with profiling. Next slide, please. So general observations from our optimization for this processor is, like the PowerPC, the 8-bit quantized was slower than the floating point, which this wasn't so surprising, but as opposed to the PowerPC, where I don't think any amount of code, optimized code, will get us faster than the floating point, for the Leon 3, I think getting an optimized core and optimized kernel available will actually help speed this up. And I think some of the reasons for that is the Leon 3 does not have single cycle multiply and accumulate floating point support. It just has a dedicated multiply. It has a floating point core, but it's not nearly as strong. So getting some integer math, and especially because of the smaller L1 cache, reducing the intermediate math size of everything will help reduce the amount of memory usage and hopefully speed up the system overall. And a note to the usability of TFLite Micro, it was relatively difficult to get it to work because it just came out of experimental on the TFLite code base. And so there's not as much support. It's a lot more specific to the platforms that they're targeting. And so I assume over time this will get better, but currently it is relatively difficult to use. And one of the assumptions that TFLite Micro uses is the fact that a lot of these processors have an L2 cache. And so that's a lot of their memory management schemes rely on that. Whereas the Leon 3 that we are using does not have an L1 cache. So that's something that we'll have to consider when moving forward. Next slide, please. So here are the metrics that we got from the various different platforms. So to kind of help interpret the graph, the leftmost column is the different platforms that we tested. At the very top is the terrestrial baseline, which does not have the throughput optimized because it's a little bit harder to get it on a GPU and a more complex system. But for the rest of them, on the second from the left column, you'll notice it says optimized. And so where you see a Y, that is where we're using the optimized model we had for that system. Where you see an N is where we use the baseline model as proposed in the research that came up with that model. And for the RAD 5545, Y with a generic next to it refers to just the generic model optimization, whereas the Y with the all refers to the performance with the source code optimization and the generic model optimizations. And then the throughput that we had was in pixels per second because all these different systems processed different images in parallel, some simultaneously, some of different sizes. And so pixels per second was the best way we found to actually normalize this comparatively. And then the rightmost is the accuracy drops that you can see from the various different optimizations, which were in the grand scheme, very minimal, with the most being 3% from the baseline implementation. Next slide, please. So this is kind of the same graph, but this time, the previous one was for the crater detection, which was a simpler problem. And this one is for the Earth imaging metrics. And you might or might not have caught that before, but for the fastest Polarfire implementation, and the crater detection was actually 21 megapixels per second. Whereas for the DSTL Earth Imager data set, it's actually 16 megapixels per second. So because we had to use a larger model that actually slowed us down comparatively, but the same ordering of speed comparisons were still true even with a larger size. The speed performance were just not nearly as pronounced as with the crater data set. Next slide, please. So that was our general research. And for next steps forward that we're looking at, one of the big ones is how to automate the optimization step. So for the current research, a lot of the optimization that we did was done by hand. So we would go through and we would analyze, the person would analyze it, see how it performed, and then take a guess of where they think it would best perform. And then we try that again in that cycle. But some of the modern research, including one paper by Google called NetAdapt, shows a way of doing this automatically by testing it on the platform and doing a lot of this optimization by testing just large amounts of different models and different sizes. And that one, we didn't have enough time to actually implement that. It was computationally expensive and a bit more complicated than we wanted to take on. And so that is a future step we want to work on. We'd like, one of the next steps too, is to produce an optimized kernel for the Leon 3 to see if we can get faster speed performances with that. And we'd also like to utilize a lot more of the Vectorblox tools that are coming out. So as they're releasing new additions and whatnot, we'd like to try the different sizes and the different operators to see how they would support for us. Next slide, please. And one of the areas that I am super excited about is exploring unconventional machine learning routes to make it even faster in constrained systems. And one area that we are focusing on right now at Southwest Research Institute is using low precision neural networks. And what that means is normal neural networks works on 32-bit floating point math for the multiplies and the additions. And a lot of the embedded systems nowadays are using 8 bits. But we can go even further to reduce the bit precisions to even smaller sizes like 4-bit or 2-bit, or the most aggressive size that is available is a 1-bit representation. So you're taking the 32-bit floating point map and turning it into either a -1 or a 1 in a single bit. And one of the really cool properties of this is when you turn it down to a single bit, multiplications in this reduced space actually can be done using an XNOR operator, and additions can actually be done with bit counts. And so this will greatly improve the speed performance of a lot of these networks. And part of the research is trying to understand, when we reduce it, how do we make back some of that accuracy loss from the lack of precision? Next slide, please. So that is my entire presentation. Thank you very much. My contact information is right there. It is my first name dot last name at swri.org. And I guess now I will start answering some of the questions.
Excellent. Thanks a lot, Ryan. Question that came in from Alan Cudmore in the chat. What operating systems were used? Linux? Was Linux used on a Leon 3 and a RAD 5545 CPUs?
Yeah, good question. For the RAD 5545, we actually used Linux. Specifically, we ended up using a Yocto embedded Linux system for that, 64-bit. And for the Leon 3, we actually just ended up using bare metal for that implementation. So no operating system was used there.
All right. And next question from Wesley Powell. Did you also look at power efficiency when benchmarking across the processors?
We did not look at power efficiency. We didn't have the tool set up, and that really wasn't in the scope of what we were trying to do. Mostly, we were just trying to see, could we make the speeds there? And then at that point, we can make an argument, and then we could hash those out in the future. But that's actually a very interesting point, because some of these automated detection systems, where you're having a system that is automatically going through and checking different options for reducing your network size, you can actually make one of the metrics that you're trying to optimize for the power. And if you could feed that back in an automatic way, there are automatic ways to actually optimize for that as you're searching.
All right, great. Next question from Joel Sherrill of OAR. Did you evaluate the memory bus bandwidth for each platform?
No, we did not evaluate the memory bus bandwidth, because we were trying to be agnostic of the system. So we didn't want to kind of constrain ourselves to the bandwidth of this system or that mission. These are definitely factors that will affect the speed, but hopefully we can design a system that will help mitigate and hide a lot of these issues by maybe pre-caching it, preloading it, and stuff like that. So that was not explored in this research.
Okay. Next question from Leonidas. Do you have any explanation or idea about why the crater case study, the performance difference between the FPGA and the GPU is increased?
I have to read that question really quick.
Yeah, I wasn't sure if there was a missing word there in that question.
Do you have any explanation for the idea about crater's performance difference between the FPGA and the GPU increased? I don't know if this will answer the question, but for both cases, the crater and the Earth imaging satellite, we did notice a difference between the two with the FPGA. The FPGA was the fastest, I would say, because it's a dedicated hardware. Something I will note is we only tested the TX1, the NVIDIA TX1, and for any of you who are familiar with that environment, the NVIDIA TX1 is also the Jetson Nano platform, but that is their lower, more efficient network. There are other embedded platforms that they have that are faster, and they will probably beat out the FPGA, but the TX1 was the closest comparison to something that would be flying in space, just as a benchmark. So I don't know.
Okay. Last question from Joel Sherrill. Is there a way to audit the decisions? And I'm not sure if I understand what that refers to, but maybe you will.
Yeah, I don't really understand what that question is
Okay,
asking.
I asked him for some clarification, so maybe that and the other question could be taken over to Slack. So we'll get those copied over. Ryan, thank you very much for an excellent presentation.